Okay, to this point, we have found the reactions, meaning the forces at the supports. Now, the next big topic we're going to cover, new topic, is that now we want the forces in the truss members themselves. So, in other words, we see that we have, each truss has a lot of different members. Now we want to know what are the forces in each member. And in the same way that when we did our reactions, we looked at the type of support that we had. And, if we had a pin, we knew that we had an X and Y. If we had a roller, we only had a Y, for instance. So now the same thing is going to be true with the truss members. What is a truss? We have to figure out what a truss member resists. And a truss member resists tension or compression. That's it. So what we're going to do then is when we draw our free body diagram and we've made an imaginary cut through a truss member, then we're going to put tension or compression, because that's it. A truss member, again, is long and skinny. It does not resist bending. It's not like a beam. So when we had our cantilever beam and we made a cut over here, what did we know? We knew that a beam resists bending, so we put on an X, a Y, and a moment because it resists bending. Well, since a truss member is a long and skinny member, it doesn't resist bending. So this is a long, skinny member, so we're just going to assume, and I've stated it before, we never put a load in the middle of the member because it bends too easily, it's going to buckle. So trusses only resist tension or compression along its axis. So that is fundamental to the way that we draw our free body diagrams. So a couple examples. Here's a bridge or a beam made out of a truss. Here is a crane boom, frequently made out of a truss. And then I'm going to point out that a true truss, now, they're not necessarily built exactly this way, but in the true truss that we are analyzing has all of the members are connected by a pin. So in other words, each node in the truss is a pin. So all of these connections here are pin connections. Okay. Crucial to figuring out the forces in the truss members is drawing the free body diagram correctly. And we're going to start this with a description of how to do the free body diagram. It's not difficult if you understand basically copy and paste, which I can do. You may or may not be able to do a copy and paste. If you don't, you have to do the equivalent of a copy and paste. So I'm going to show how to draw this free body. Here's my truss, and here I'm going to illustrate how to draw a free body diagram. Here's my dashed circle or dashed loop. I want to draw that free body diagram. So, and if we look at it, what we're going to see is, where do we make cuts again? So we're looking at cuts. So for this particular free body diagram, what we see is that we've made cuts. I made a cut here, through that member, through that member, through this member, through this member, through this member, this member, this member. So we're making all of those cuts. Now, remember, everywhere we've made a cut, an imaginary cut, we have to put a force or forces. This is the basic concept of everything we're doing here practically. So I am going to make my free body diagram, and I'm going to, once I've made those cuts, I'm going to put in a force or forces. Well, so I'm going to do my copy and paste, and so I'm going to trace my dashed loop like that, so that traces my loop. And now I'm going to say copy, and then I say paste. So I now begin my free body diagram with this. In other words, I have to draw exactly what is inside my dashed loop. And that's what I've shown. And by the way, I have to include all the loads in this thing. I can't, in other words, I can't draw my dashed loop like that and get rid of that load, and I can't come in here and get rid of that load. I have to include the loads. So, so they are there. This is what I have here. Right here is what's contained in my dashed loop, and then I look for where I've made my cuts. Well, I made a cut here, so I put a force there. I have a force here, a force here. I made a cut there, so I have a force there, and a force there, and a force there, and a force there. I have all these forces, and I'm showing you how the traditional way that we do this for truss members is that we always draw a force parallel along the axis. So in other words, I have to draw along the axis of my truss member, and then I show an arrow away from the truss. So that's so the correct way to draw this free body diagram is like this here. And I can label each unknown force like this. And traditionally, in these statics class, we have these labeled in letters, and then we have the force, and then it doesn't, from B to A. So I've got B to A, member AB, member BA. It doesn't really matter whether we call it member BA or member AB. It's the same thing. So it doesn't matter. In this case, I'm calling it FBA. FAB, FBA, same thing. So, and then this one goes from B to E, C to E, F to E, C to G, F to G, C to D. So that's how we're going to label these. There may be other labeling schemes, but this is the way that I want you to do it in this class. So you need to follow the method that I'm using here, so you need to label it in that manner. Okay, so just to let you know that in practice, we run out of letters. So generally the nodes are numbered instead of lettered. But for some reason, traditionally in this class, we always use letters. It avoids the issue of too many numbers around and getting confused with the numbers. So nodes are labeled with letters, and then we label our forces F, and then the two nodes that the truss member spans from. Okay, so, and then again, this force has got to go parallel. Why does that force have to go parallel or along the line of the member? Well, it's got to go along that line because a truss member only takes tension or compression. So tension or compression is along the line of that member. You know, like we said, if it's a hinge, we put an X and a Y force. If it's a roller, we put a Y force. If it's a connection to a wall for a cantilever beam, then we put a moment and an X and a Y force. So it depends on what we're cutting. What you have to recognize is what we're cutting with our free body diagram determines what we put. And in this case, we're always cutting truss members, and so I put tension or compression at each member. And then the other thing that you need to do, if you can't use the copy and paste function, then you need to draw exactly what's inside. So you need to draw this. If you don't have a copy and paste function, you have to draw exactly what's inside here by hand. I can use the copy and paste function, but you have to end up with exactly, to get your the beginning of your free body diagram, you have to put down exactly what's there, what's contained within this dashed loop. Okay, and then once again, you draw exactly that, and then you put and label the forces going away from the from the member. So in other words, don't draw it that way. Don't draw it that way. There's nothing wrong with doing it. It's just that nobody does it that way. So don't draw them toward the truss member. Don't do it in reverse like that. Everybody, this is the convention, and you need to follow the convention. Like I say, I'll take points off if you don't do it this way. You need to draw these away. Away. Away is pulling. Away means tension. So the way that you think of it is, if you take your arm and you pull on something, then your arm is, you're going to see your arm is in tension. If I take and I pull on something, my arm is in tension. If I take my arm and push on something, then what happens? Well, my arm is in compression. So I'm going to show pulling away. Okay, it's not to the left, it's not to the right, it's not up, it's not down, it's just away. That means tension. So, yeah. So this is the convention used by everyone, is to draw the unknown member forces pointing away from the node. Away from the, in other words, the node is here in a sense, and I'm pulling away from it. The node is here, I'm pulling away from the, and that tells me what? Just to let you know what we're getting to is that after I solve for this thing, if I get positive numbers for all of these, then all of them are in tension. They're in tension. Anything that I get when my end result, if it's positive, then the member is in tension. If it's negative, then the member is in compression. So it just makes our it just gives us a standard that we can use, and we see immediately when we get a negative number for one of our forces, then that means it's compression. That's so. Okay, so here's homework, and then draw the free body diagram shown by the dashed line. So here's my dashed loop. You have to look closely here. Is exactly what. So what you need to do, so I'm going to tell you in advance, if you don't have a cut and paste function, then you need to draw exactly exactly what is contained in this loop. So you got to start there, exactly what's contained in this loop. Draw that. That's the first thing you have to do if you don't have cut and paste. Okay, pause the video, do that. Okay, so I'll just do it with a copy and paste. So again, I'm just going to come in here. I'm going to follow my loop. Exactly. Oops. I made a slight. Okay. So I do a copy, I do a paste. And there I am now. I got a little bit messy because I got the got a little bit of the loop, but that's all right. What I now want to do, I'm just going to clean it up a little bit, and well, I accidentally this is only clean it up here, and in this I accidentally made a cut where I wasn't supposed to. This is not a cut there. Okay, so what do? I'm looking at this, so, and now I'm going to see where I made cuts. So let me get a different color here. And where did I make my cuts? Let me just label this. This is 40 kilonewtons, so I have to keep the forces. I cannot cut around the forces. But notice I made a cut right there, so I have to put an FAB there. I made a cut here, so that's going to be an FBE. It could be FEB, FB, doesn't matter. This one is an FEC. And this is an FFC. And this is an FCG. And this is going to be an FCD. And an FDH. And an FGH. So that's the methodology. I drew it up there so you can see it, but it's the same. It's the same as what I have here. So this is all you have to do. So all I want you to start with is to be able to just draw this. Don't have to do any calculations right now. Just be capable of doing that. And like I said, all the unknown forces are pointing away from the node. So notice I didn't draw this force going like that. I didn't draw this force going like that. It's pointing away. They're all pointing away. That's what we want, because that's pulling away, pulling, not pushing. This is pushing. This is pulling. If it's pulling, it's in tension. So if I get a positive number for this, then that arrow is correct, and I have tension. If I get a negative value, I flip the arrow around, it's compression. And like I say, this is the convention that everyone uses. Another homework. Now draw this free body diagram. So pause the video, draw that. I do the same thing here. Come in, I do a copy and paste. copy, paste. There it is. I'm just going to make it a little bit bigger. And then what do? Then I come along and everywhere I make a cut, I put a force. Looks like that, and then I simply label the forces. So that's all there is to it for this part, but you have to get this part right. And we end up with this, and then, you know, node to node, BC, CE, FC, CG, DG, HG. So you just label it properly. Okay, so hopefully you have understood here how to do these free body diagrams. Now, there's a lot of unknowns here, so that's not good for us. So we're going to draw different free body diagrams, but the concept is going to be the same. All right, so the first thing, so let's do this problem. We're going to start with just simply finding the reaction. So here's like the easiest truss we can have, which is a triangle. That's the easiest truss you can have. The simplest truss is a triangle, a single triangle. And first thing we want to do is find the reactions. Well, we've done this a million times, so I'm not going to dwell on it. Here's my original drawing. Here's my initial free body diagram I have for the pins, CY and CX. For the roller, I have BX. And now I want to find the reactions. So I can take moments about B, and I get moments about B. That eliminates CY, eliminates BX. And so I just have CX times this distance, which is 3. Then this line goes through the point, so I don't consider it. That line goes through the point, I don't consider it. And then I have this 10 times 2. So CX times 3, 10 times 2, and what are the signs? CX is clockwise around BX, so that's positive, and this 10 is counterclockwise around B, so it's negative. So it gives me CX times 3 minus 10 times 2. We get CX is equal to 6.67. Take moments about C. Take moments there. So all I'm going to have is a BX and a 10. So it's going to be BX times this distance, which is 3. So BX times 3. And then we have 10 times this distance, so it's going to be 10 times 2. Right there. So I have, well, this is going to be clockwise, so it's plus. This is counterclockwise, so it's minus. Minus 10 times 2 plus BX times 3. I get BX is equal to 6.67. And then, well, I just take the sum of the forces in the y direction. It's quite simple. This is this is 10. This is CY, so it's going to be negative 10 because it's going downward. That's CY. And So it's minus 10 plus cy equals 0. And we get cy is 10 kips. Now we want to find all the member forces. So this is the harder part of it. In a sense, it's a little bit different. Now the way that I'm going to make these free body diagrams, I'm going to make this first one very simple. I'm just going to make a cut around that point. So again, I do a copy and paste. I end up with this. So I end up with, you know, these little members there and the force. And remember, I have to put I need to put my unknown forces here. Yeah, I guess I chose this point first. So maybe let me just do that one first. Okay, so I draw my free body diagram from that. I have this little tiny thing right there inside my loop with the 6.67. That's what I have. So I have the little tiny loop with a 6.67. That's my original free body diagram. Then I add on my FBC, FAB for this member and this member that we have. And so this is my free body diagram. And if I look at this, I'm going to get two different things. I can take the sum of the forces in the y direction equals 0. Well, there's only one force in the y direction. So I end up with FBC equals 0. So what does that tell me? Well, that tells me that there is no force in this member. That's using the sum of the force in the y direction. Sum of the force in the x direction, what I find is I'm looking at my picture and I have minus FAB minus 6.67 equals 0. And I solve for FAB, I get negative 6.67. Now, what does that tell me? That tells me that my final FBD looks like that. And what does that tell me about the nature of this member? Well, this member is going to be in compression because it is pushing toward the point. So the member is in compression. That means what? That it's in compression over the entire length. What we're assuming is that the force in a truss member is the same everywhere. So if it pushes with 6.67 on this point, it's going to push with 6.67 on the other point. And so I am going to take free body diagram of this point. I'm going to show the 10 kips is here, an external load, and I don't know what FAC is, but I do know that this is 6.67. So now what I'm going to do is I'm now going to solve this. The easiest way to do this is to replace any loads acting at an angle with an x and y component, and we've done this a million times now. This angle, this little tiny angle in here, is 50, you can all figure this out, this is 56.3 degrees, and so I'm going to take these and use components. So what I have, this is upward to the right, so I have upward to the right. And it's going to be FAC, FAC sine 56.3 for the vertical and FAC cosine 56.3 for the horizontal. And then I look at this, I take the sum of the forces in the x and y direction. So I just look at this picture. What do I have in the y direction? I've got these two here. So I'm going to have minus 10 for this one, plus FAC sine 56.3 equals 0. And then I look at this drawing again, and I have okay, man, something went awry here. Oh, there we go. So I take the, so I get FAC equals 12 kips at that, and then FAC is 12 kips, and then I know what FAC is, so it's 12 kips. I have 6.67 kips. That comes from this one, and this shows compression, which is correct. How do I know it's compression? It's pointing toward the point. This is pointing toward the point. So the member all the way across its length is in compression. It doesn't switch from one thing to another. If it's in compression at one end of it, it's in compression at the other end. If it's in tension at one end, it's in tension at the other end. So I have to be consistent here in other words, if this is 6.67, this is 6.67. Why? Because I'm looking at two different points on the same truss with the same member. I'm still looking at that member FAC. So it doesn't matter if I'm looking at the right end of FAC like this or the left end of FAC like that. It's the same. Once I figure what it is, then sorry, I'm calling it FAC. It should be FAB. FAB is 6.67 compression. So let's look at the what we know then. We know that what we've determined is, if we go back here, we found that FBC was 0. So I now have all my members, right? Because I have FAC, FAB, and FBC. That's all I have. So, because I only have 3 members here, right? And I figured out that FAC is 12 kips. FAB is negative 6.67 kips, and FBC is 0. So I have figured out all of my forces for all of my members, and then now I just want to represent it basically, and so that's the next example, is to use the final FBDs to draw the final FBD of node C and draw a final FBD for each truss member. So I'm just going to show you what we end up with. We've already shown this and we've shown that, and I can take these and put them in my drawing. I'm going to put that there. I'm going to take that and I'm going to put it there. And I'm going to take these two that I've already figured out, I'm going to put them here. And then I'm going to fill in the rest of the drawing. Here's my truss. Looks like that. And to be clear on how this works, we have, let's take this member here, FAC, or take member AC. I have 12 kips pointing away from point A, meaning it's in tension. I have also, it's got to be the same, 12 kips pointing away from C. It's got to be the same 12 kips, and it's got to be pointing away, again, in tension. Now, what I have here is what's happening at the node. This is what's happening at the node. What's happening in the actual member is, and this is an important point, so I'm making cuts of the member. So in other words, I can come in here and I can draw a loop around here. Just draw a loop of the member. And what does that look like? So that's what this represents. That's what this represents here. Well, if it's 12 kips at the node in tension, what we find, these have to be equal and opposite. These have to be equal and opposite. Because what I'm doing is I have adjacent free body diagrams. In other words, I have this free body diagram at the node, but it shows part of the beam. And I have this, same thing. We have the free body diagram at the node, but it shows part of the beam. And it shows that this is 12 kips tension. This is 12 kips tension. Then to be compatible, this member here also has to show 12 kips in tension, which it does. So these have to be equal and opposite, equal and opposite. Same thing with the other ones. This has got to be equal and opposite, equal and opposite, equal and opposite, equal and opposite. So what this illustrates is we've taken these nodes, the free body diagrams at the nodes, and shown what this looks like for the entire truss. So that when I look at this, I can clearly see that member AC is in tension, right? Because the arrows, of course, are pointing away from the member, and that means that the member is in tension. Here, these members are zero, or these forces are zero, so that means the member has zero forces. So it doesn't matter, well, zero is zero, put it that way. So, okay, and then so this picture shows the whole thing, and since, like I say, we can see that member AB is in compression. Why? Because it's pushing to the point here, but then let's take the free body diagram of the middle. It means what? It means I have to flip the arrow around and point toward it. So this is going toward at 6.67, toward at 6.67. Oh, we have this in compression. So, okay. Long story short here, hopefully, this is the longhand method, but what you're going to see in practice is you're going to see that shorthand. This is in shorthand. So these two things are the same thing, but the shorthand just shows the nodes in a sense. So in other words, I got this, that's this. I've got this, that's this. I've got this, that's this. That's the way that it's drawn. They show the nodes. You need to be able to interpret that, that when you see this, that means it's pulling on the node. You got to look at the nodes, pulling on the node. That means this member is in tension. And here, this member is pushing on the nodes. If it's pushing on the nodes, then this member is in compression. So I don't necessarily like this shortcut, but that's what you're going to see. And this is an example of it for a different truss. You can see that, you know, how about this one? Is this member in tension or compression? Well, it's in compression. Why? Because it's pushing on the nodes. And same thing for this one here. It's pushing on the nodes, so that member is in compression. In this particular case, if you look closely, they have sort of color-coded everything. So the green ones are in compression. They're pushing on the node. The red ones are in tension. They're pulling on the nodes. Okay, I'm going to stop.